So in this clip, we're going to look at the orthogonal decomposition of an inner product space. So this is like one level up from what we were doing before. If you go back to, what was it? I think it was 6.A.7 and compare. That's where we did an orthogonal decomposition of a vector. Now we're doing an orthogonal decomposition of a whole dang vector space, right? And so the way it works is that if U is a finite dimensional subspace of our inner product space, then U direct sum its U complement gives you V. So in other words, V splits into U and the other stuff in a direct sum. And you can also think of this as an extension of what we saw in theorem 234 once long ago. It said that given subspace U of V, there is a subspace W such that V looks like U direct sum W. And so this is now just saying, oh, you know what? You can do that decomposition orthogonally. So, because it's possible to do it with a non-orthogonal subspace as well. But if you're in an inner product space, you can do it orthogonally. And by the way, let me just point something out about this decomposition right here. It's easy to make the mistake of thinking about this as a union if you're just new to thinking about orthogonal complements. So if you imagine like in R3, right, we've got something and then we've got its orthogonal complement, so that would be like this guy. So here's two subspaces. I've got a two-dimensional space here, and I've got one-dimensional orthogonal complement to it right here. And then there's lots of points that are neither in U nor W, right? Like this point out here, this guy is he's the sum of this thing in W and this thing in U. Oops, shouldn't have labeled that. So this point X right here, X is not an element of U, and also X is not an element of U perp, right? Okay, so the thing I was saying is that this, so V is not equal to the union of U and U perp. It's equal to the direct sum of those. Big difference, big difference. Okay, so we can also think, by the way, of this breakdown as being a spiffified version of the fundamental theorem. So this one's in the book as 322. I described it, however, a bit different. I described it in terms of subspaces instead of just dimensions of those subspaces. So I told you things like V looks like the null space of the transform orthogonal direct sum some other thing. And now we're going to see, okay, yeah, that's the null space of T perp. But in forthcoming chapters, we will get a new name for this. We will see that this is actually related to, there's another way to describe this, which is very important. So that's just a preview of coming attractions. All right, back to the theorem, enough blabbing, let's do the proof. So the proof. So for the proof, let's see. So we're going to do basically the same kind of thing that we did back a couple clips ago. We're going to say let E1 through En be an orthonormal basis of U. So then the first step is to show that it's a sum, and then we'll show that it's a direct sum. So first we will show that anything in V can be written as a sum of something in U and something in U perp, right? And so the trick we're going to use for this is the dastardly thing where we're going to take V and we're going to write it as U plus V minus U. And by the fact that the U's cancel on the right side of this expression, it's stupidly true. So the way that we're going to do it, however, is with respect to the decomposition according to this orthonormal basis. So given V as, given V in capital V, we know that we can write V as V against E1 times E1 plus da-da-dee-da-da. And then this is going to be V against En times En. So this whole schmear will be our U. And then the missing thing here is going to be V minus U. So I'm going to have V minus, and then I'm going to take a copy of that whole stinking thing, copy and paste, boing. And then this will be my W. Okay, so define U and W like this. Okay, so U is the part that's made out of the, it's the part that lies in U, our subspace. Okay, so yeah, maybe I'll just write that down. Then clearly U is in the subspace that we're interested in. And now to see that W is in U perp, we do the calculation. So if we do W against any of the orthonormal basis vectors for U, let's call it EJ, then this is going to be, well, let's see. So now we're going to have V minus the sum of V against EK summed over K times EK on the one side, and then we've still got EJ on the other side. And you know what's coming next. You can smell it. We're going to do some arithmetic with inner products. So what can we do? Well, that thing on the left is a big fat hairy linear combination. So I can split it and I can pull out the V EJ part, and then I can have minus the sum of the V EK EK EJ part like this. But I can in fact use linearity here as well, and in one fell swoop I can pull it out in front, because there we go. I can take linear combinations out of the linear inner product. Ah, let go of the stupid thing, you jerk. There we go. Okay. So it looks like this. And now what do we have? Well, when we do this summation, you can see that a goodly amount of these guys are going to die. We're only going to have a non-zero term in the case when J is equal to K. And when that happens, this whole thing is going to become 1. And so we're going to pick up the 1 when K is equal to J right here. And so this is not actually a sum anymore. There's only one non-zero thing left. It's the one when we have that this entry is where K is equal to J. And pow! Dead. Okay, so that shows us that W is orthogonal to EJ. So in other words, W is orthogonal to every basis vector of U. So that means W is orthogonal to U. Or in other words, W is in the orthogonal complement of U. All right. So this shows the first part, namely that V it can be written uniquely as something in U plus something in u perp. Sorry, it can be written as a sum. The uniquely part we have to verify yet. But that actually we just did in the last clip. Okay, so since u cap u perp is 0 by the previous clip, or the theorem in the previous clip, then we know that this is an orthogonal direct sum. Sorry, that it's a direct sum. Yeah. Okay. End of proof. All right, we have a quick corollary. Corollary 650. And that is that if U is a subspace of V and the dimension of V is finite, then the dimension of U perp can be found by subtraction. And this is just a restatement of a result that we saw before for direct sums. The only thing that we're saying now is we're replacing W with U perp. So there's not a whole lot of excitement going on there.